All right. Good evening, everyone. So for one of the extra credit projects, which is option 2, we're going to be looking at what is called a Fourier series um, from this varying peak sound wave. And I'll try to do my best to make it as simple as possible because, you need to reproduce this yourself for a problem. But you can just think of this particular wave. It could be any form. It could be a triangular wave, a sine wave, cosine wave, or a wave that looks like this. This wave right here is made up of a series of other waves that once you add them up together makes this wave. And so this function below is basically describing that mathematically. In order to get to this function, that would take too much time and make the video longer than it needs to be. But basically this function here mathematically describes a superposition or an addition of several waves to make this wave that you see on the screen. And so we're going to use math to extrapolate what those waves are, right? So that's the purpose of this function that we see here. So let me go through and itemize all of the letters, the variables here. So, all right, so what is this L, these bounds here? So when we have an integral, those in calculus would know what I'm talking about without even, thinking about it. But an integration symbol is denoted by this guy here. And the lower bound is where it starts from, like the initial position. And then the L is the final position. Well, for the sake of argument, we're going to call L half of the wavelength. There's a particular reason why. I guess I can talk about it. I can't really go off, cannot go off on, not go off on that tangent. But anyway, a full wavelength would be the distance between two similar points. It would be the distance between, say, this point here and this point there. And the length L would be 1/2 of that wavelength. Just imagine that you had a guitar and you had a particular string on that guitar and you just, you plucked it or you raised one of the strings and held it in place and then let it go. What happens is that over that particular distance L, the string vibrates in place. It forms a standing wave. But understand that that wave that gets formed is half of a full wavelength. So basically what I'm saying in terms of what you see here on this picture is that the length of that particular wave would just be from 0 here all the way covering this distance right here. So we're going to call the length L 1/524. And these numbers here represent the seconds, the time in seconds for this particular wave to vibrate space. So this integration is going to be with respect to time. We can have an integral with respect to space. We can have it both. But, just for this particular example, we're just going to do time. All right. So this length L, we're going to call 1/524. That is the length of this particular string or wave that we see in this picture. And it's very similar to what I was describing just a moment ago. Is, let's say we take a guitar string and we held it in place, we held it up, and this will be the length L. And so that's half of a wavelength because a full wavelength is made up of a crest and a trough like that. So we've seen that back in chapter 15 of our text when we're talking about wave mechanics. So this would be from here to here would be a full wavelength. So right here would be 1/2 of that. And so this basically, this length L that we see here is equal to 1/2 wavelength. And thusly, it's 1/2 a period as well, because a period of time corresponds to a full wavelength in space. So that's why we can do this integral in terms of space and time. We have to do them separate. That's something that we call a separation of variables. So I'm speaking and talking and all this right now. Don't worry about it so much. I'll get to the specifics, but I'm just letting you know what you can do with a function like this. You can integrate it with respect to time or integrate it with respect to space. You can do both and have a function that describes both space-time coordinates. All right, and then you can do something called a Fourier transform to go between the two. All right, so I tend to go off on that tangent. Okay, so just bear with me here. I'm trying to, give you some of the basics in the background, and well, try my best to keep the video short. Okay, so the first thing that we wanted to establish is the length of this particular wave, which is 1/524. We have our function. I shall write it again. P of t, like f of x or whatever, pressure as a function of time, 0 to L, those are our boundaries. And this B sub n, these are what are called coefficients of this wave function that we see here. And the wave function is going to be sine n pi x over L. The L's, these are the same L's, and it's going to be integrated with respect to time. So again, the B sub n's, we're going to find those. In this video, we need to find all of the coefficients that correspond to the all of the wave functions that make up this wave that we see on this screen. So basically, there are going to be many waves to make up this form. So just think of it as like you're, let's say, for instance, you're taking a microscope and peering in close on this sound wave, and you're seeing all the waves that make it up. Like you see the number 4, and you can peer in and see 2 + 2 or 3 + 1, all of the different combinations that make up that number 4 that you see. And so that's basically what we're going to be doing here. We're going to be extrapolating all of the waves that make up this particular pulse. And this is basically a mathematical / physical precursor to what a radio signal from a broadcasting station does, or you can send a signal out, and then you can tune in to the different frequencies of that signal. And so by doing what we're going to be doing is called Fourier analysis, to see all of the different waves, all of their different frequencies that make up this wave and its particular frequency. So we're doing the math here, and then the engineers create their RLC circuits to correspond to what is called to make sure that those broadcasting stations can resonate with whatever we tune into. So basically, at your radio, you're tuning into the particular frequency, one of the frequencies that this signal has. And so once you do that, you're resonating with one of the frequencies, and then therefore you can hear the radio station. So we're going to do the math of that. The engineers put it all together and based on what we do here. So we have to get this right in order to go to engineering department. They do their due, right? Okay, so the B sub n's, as I mentioned, these are the coefficients of the wave function. So just think of them as the number before the wave function, 2 sine n pi x over L dt. And there's a particular reason why this sine function looks like this. Again, I'd have to be extrapolating backwards to make another video that precedes this one in order to figure out why this function is. But again, that would take too long. And I'd rather just start with this function right ahead. So how are we going to find those coefficients? Well, we can take this function and solve for the B sub n's. But before I do that, I want to describe the other variables. So if this is a sound wave or some kind of pressure wave, some kind of waveform that's produced by something physical like sound or air or whatever the case is, and then we have an oscilloscope that's allows us to see the particular signal that's made from, let's say, especially a sound wave, then that sound wave would basically have this form. Okay, so this would be pressure as a function of time. And then this sine n pi x over L is the actual wave function, which we'd have to solve for. You know, just think of a mass on a spring. We can solve for this, and there's a reason for this form. It goes into boundary conditions where the sine function works instead of the cosine function based on what conditions that we have. And what are the boundaries? The boundaries are 0 to L. So, and with these boundaries, the sine function works. With another set of boundaries, the cosine function works. So anyway, sine n pi x is a wave function, and dt is what is called the integrand, or the variable by which you're integrating over. Term notwithstanding, you know, not worried about that. But this is basically the integrand or variable you're integrating over. Because basically what you're going to do here is take all of these moments in time, these dt's, you're going to sum them all together to get a particular result. So, you know, just think of all these little time intervals, ti, t1, t2, t3, t4, and you're just integrating each of these what are little rectangles together to get the entire time t. Anyway, this is dt is the integrand, or the variable of integration. Again, the terminology is trivial. I don't care what it's exactly called, but it's basically what this is. And when you see something like this, obviously you're going to have to perform an integral over this wave function. And let me not be remiss of this. Let me get this out of here, because I'm thinking space. If this was space, it would be dx. Since this is time, this is going to be n pi t over L dt. So let me erase this here. N pi t over L. We'll see how that easily fits when we do the integration itself. So that's our setup. So how would we find these coefficients? So the formula that we're going to use to solve for the b sub n's, where n is equal to 1, 2, 3, they're integers, and so these coefficients are going to correspond to different type of sine functions, because there has an n in there as well. So these are going to be particular sine functions with their coefficients to make up that huge green wave you saw on the previous screen. So so the b sub n's are going to be found by using a Fourier series equation, which is this particular type here, 0 to L. And we're going to say this is going to be P of t sine. So basically, we're just swapping these two. There's a particular reason why. You don't need to really get all in the weeds on that, but it deals with complex conjugates and other things that I would easily get on a tangent and make this video too long. But anyway, we're just swapping those two variables. That would be n pi t over L dt. And when you're doing something called a Fourier analysis or Fourier series, depending on the boundary conditions, you're going to get a particular type of Fourier series function. And for this particular boundary conditions, this Fourier series function works. There are other boundary conditions or other Fourier series equations that work for other boundary conditions. Like say, if you're going from 0 to pi or negative pi to pi, there's going to be a different type of Fourier series equation. But since our boundary conditions are such as these, 0 to L, we just have, we're basically in a box and we're starting from 0 and going to the length of the box L, we'll use this Fourier series equation. to get our B sub n's. And those B sub n's will help us get all of the waves that make up that green wave function. Okay, so now what we must do is to be careful, and this is where the video may get long, but it's important. So I don't want to be too fast just because you need to have it under 30 minutes. I know I said that in class, but this needs to stretch as much as it needs to. So let's go back to the first picture. So we have to be careful of how we are going to use that integral with all of these numbers that are on our screen here. So let me put some numbers on the y-axis here. Let's call this 1, and this little blip here, we're gonna call 7/8. This is 7/8 of the whole. And we're gonna put this one down here as the corresponding negative 7/8. And this would be -1. So we have to get all these numbers so that we can perform the proper integral. Well, this B sub n's, this is the main function. So we know that L is equal to 1 over 5/24. So 2 over L is going to be 2 times 5/24. So you're going to basically see, this is going to look like this. 2 times 524. And now we're going to go from 0 to the length, which is 1 over 5/24. And then we put in our P of t function. It's an arbitrary function that we'll deal with, accordingly. So P of t, and we're going to say sine of 1 over L, which is 5/24, because L is 1 over 5/24. So 1 over L is 5/24. So this will be 5/24 n pi t. So see, so we've already taken care of the L. So now we're going to have the n pi t. Sorry, I'm going to have to squeeze it in like this. N pi t dt. This is all one line, guys. Maybe I can write it better. There's a lot of little variables in there. Just squeezed in here. Okay, make sure my setup is good so I can write effectively. Okay. All right. Bear with me there. I may pause and all that stuff to make sure this edit's okay. So 2 times 524, 0 to 1 over 524. And P of t is arbitrary, we can actually just throw it out. We understand it's going to be there, so it doesn't matter what it actually is. We know that it's part of the integral. Sine 524 n pi t dt. Now, this part, my mouse over here. Okay, so this part of the function describes the wave as it goes from 0 to 1. Okay, so we have 2 times 524, and that's the upper bound or the highest part of this varying peak wave. So 2 times 524 is going to be 1048. So how we're going to integrate this is from the highest peak to the lowest peak over the distance L. So the highest peak is at 1 minus the lowest peak minus 7/8 times 2 over L. So let me go back here. So remember, we have 2 over L. There are 2 regions for 2 over L. It's the upper peak at 1 and the lower peak at -7/8. So that entire integral is made up of 2 parts. This upper part and this lower part. And all we're concerned about is one length, because we know it repeats itself. So we don't have to do all the parts. Obviously, for those who are calculus aware, we don't have to do that. We just have to pick the boundaries accordingly, integrate that for this space. We got our answer because we know what answer we get here, it's going to repeat every 2 pi radians or every 1 over 260 seconds. So this is basically our 2 pi that, you know, that we normally see in our periodic sine and cosine functions. So we just have a different period, 1 over 262, and it repeats 1 over 262. So again, we are integrating from the upper bound or the maximum region to the lowest. So this here would be 1048. 2 times 524. And since that is the upper region, okay, since this is the upper bound, our boundaries are going to change for this upper bound. So let me go back and repeat a couple things. This integral right here is the whole integral, right? Because we're going from 0 to the entire length, L. 0 to 1 over 524. Well, that entire length is made up of 2 pieces. 0 to 1 over 1048. And then we're going to integrate from 1 over 1048 to 1 over 524 to complete the journey, to complete a full length of 1 over 524. So we're going from 0 to 1 over 1048 minus 7/8 times the function that we're going to see again, minus 7/8. And the integral bounds are going to be from 1 over 1048 to 1 over 524. Again, our boundaries, I guess I can put it here. This entire function that we saw, which is going to be 2 times 524 times all that stuff, 0 over 1 524, it's going to be made up of 2 regions. And we have to account for that because of how the wave is. Let me see if I can scroll down. Scroll down here. Okay, 1 second. My smartboard is acting up. I'll be right back. Okay, so a little bit of fixing that up. Okay, so like I was saying before, we have an entire length that goes from 0 to 1 over 524. So maybe it was a good thing that had the malfunction, just to repeat things. So this entire length, 0 to 1 over 524, which we've established here, is going to be made up of 2 pieces. 0 to 1 over 1048. That's our maximum peak. Then our minimum peak is going to go from -7/8. Well, we're going to incorporate that. But the boundaries are going to go from 1 over 1048 to 1 over 524. And so let me just put that into this guy here. So this is the full function that we get from here. And now we're going to break this full function into its pieces. 2 times 524. Let me just go ahead and be explicit about this. Also, now you want to mess up again. Okay, one more second. Okay, hopefully we can get this all in order. A little bit of some technical difficulties there. Okay, so like I said before, these b sub n coefficients are going to be solved by using this whole integral. It goes from 0 to this length L, and that length L is broken up into two pieces that are held by the upper bound, which is at 1. And that's going to be multiplied by this 2 times 524. And that's going to be an integral from 0 to 1 over 1048. Just to repeat, why is it 0 to 1048? Because the highest peak goes from 1, the highest peak goes from 0 at 1, goes from 0 to 1 over 1048. And then at 1 over 1048 is the lower bound, which we will account for with this negative 7/8 here. It goes from 1 over 1048 to 1 over 524, and we have the full length of this sound wave. Okay, so now just to put all the pieces in, that will be sine 524. So I'm just basically taking this up top again. N pi t dt. And then that's going to be subtracted. Why subtraction? Because we have the lower bound at negative 7/8. So it's going to be a subtraction. And that's going to be negative 7/8 times essentially this here. I'm just doing the explicit detail. We can see that that's going to be 1048, but I want to spell it all out. And that will be an integral from 1 over 1048 to 1 5/24. So we have completed the journey from 0, 1 over 1048, 1 over 1048 to 1 over 5/24 for the entire length. This is the big picture. These are the pieces. So then put in the function once again, sine 524 n pi t dt. Same function, two different boundaries. So it's still the same pulse wave. That's why the function doesn't change. It's split up into two parts because we have a max and a min that cover the entire span of 1 over 5/24. That's the long and short of that. Okay, now we're getting ready to form the very detailed algebra and integration. Okay, I'm gonna take the first piece, this guy up top. I'm going to integrate all of this. So that is going to equal 1048, 2 times 524 times 1, 1048. And now, the integral of this particular kind of sine function is going to be a negative cosine. If you're familiar with that from your calculus classes, those in calculus, but it's a particular form of negative cosine. So the integral of sine 524 n pi t looks like this. Negative cosine 524 n pi t over 524 n pi. All because of the n pi part of this, where we get this particular kind of result. This is cosine x or sine x, negative cosine. So it's a special looking kind of sine function that gives us this particular kind of result, negative cosine function. Okay, so we box that up into the boundaries from 0 to 1 over 1048. Now, you might be asking yourself, saying to yourself, okay, I haven't had, those who are choosing to do this, I haven't had calculus, so do I need to know this, where did this come from and all that other stuff? I'm just giving it to you real straight. This result that we see here is basically the operation of this entire function in here. So all you need to worry about, if you're not familiar with calculus, is just use this result. If this was 766, it'd be negative cosine 766 n pi t over 766 n pi. Just look at the pattern and not worry about the minutia if you're not in calculus. Just notice the pattern going from sine 524 to this. You're just repeating the pattern. Don't worry about what you don't know about it. Just repeat the pattern. Okay, so how do we deal with this? There's a, once we have this, we have to deal with the boundaries, the upper and lower limits here. So this is how we do that. So now I'm gonna, have the understood 1048. It's gonna operate on everything inside. So what I'm gonna do is operate on the inside, expand everything out. 1048 is gonna be just understood to be out there, so I'm not gonna carry it through. So I'm just going to worry about what's going on in here and bring back the 1048. So the first thing that we do is we take care of this function at the upper bound, right? And these boundaries, or these limits, whatever you want to call them, correspond to time t. Why, Mr. Kelly? Why, Mr. Kelly? Why do those boundaries correspond to time? Because it's a time axis, and all of these numbers are times, right? So that's why. So we're going to put everything here in terms of t, in place of t. All right, so negative cosine 524 n pi, and not just t, we're going to substitute 1 over 1048 divided by 524 n pi. So there's our first box. And so like we did in kinematics, we're going to subtract the final. This is the upper is the final. You can say this is TI and this is TF, right? Like we did for delta X, final minus initial. This is final minus initial. So this is our final result case here. Again, we've replaced 1 over 1048 or T with 1 over 1048 here. And then we're going to subtract from the same function with 0 now. So we're going to subtract the same function. Remember, this minus sign always stays around. So it's going to be negative cosine 524 n pi times 0. N pi 0 divided by 524 n pi. Okay. Now we're ready to just do the algebra on this. So what we're going to do is we're going to say negative cosine 524 divided by 1048, two numbers, and that gives us negative cosine. Let's see, n pi 524 over 1048. 524 is 1/2 of this, so it's going to be n pi over 2. Cosine of pi over 2, is 0. We'll go with that accordingly. Okay, 524 n pi. And that's going to be minus minus, so plus cosine of blah, 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 blah. This is a 0 here, so basically cosine of that. That's just 1. So there'd be 1 over 524 in pi. So this is our big box here. Now remember the 1048 was hanging outside. We'll be dealing with that because this 1048 here is, remember, it's always hanging out. So this 1048 is going to be distributed. So this, basically you can take this factor on the outside. It's going to be 2 divided by n pi, but we'll get there. And one step at a time. It is very important for you. You need to go back over this video, but it's very important for you to take this function. It becomes this as a result. Sines become negative cosines, the integral of a sine function, a particular type of negative cosine. So negative cosine 524 n pi t over 524 n pi. If this was cosine, this becomes sine. I think I'll just give you another sine function one so you can follow the exact pattern, right? I can give you an even function and then, it gets all crazy, right? All right. Since I mentioned the term even function, I'll give you a slight segue into what are even functions and odd functions. But before that, I'm gonna solve this. So this becomes negative cosine n pi over 2. Why is that? 524, this is 1/2 n pi over 2. Divided by 524 n pi plus 1 over 524 n pi. So you can see we can distribute that around. And I'm going to leave that there for now. That's my first circle. This is basically the result of this first part of the integral. Now I'm going to go to the 7/8, minus 7/8. Same process. So then I'm taking the second part, minus 7/8 times 1048. Because remember, this is the lower bound peak. This was 1 times 1048, the maximum, and this is the minimum. It goes max, min, max. It just alternates back and forth like this. Max, min, max, max, min, keeps going, and so on. Periodic. Okay, so then cosine of 524 in pi t divided by 524 in pi. And the boundaries are 1 over 1048 to 1 over 524. Okay, so this now again becomes algebra. We're going to take this function and evaluate it from the final condition minus the initial condition. Like x final minus x initial, e final minus e initial. It's all that really. It's displacement, but in integral form. So negative 7/8, 1048, and again the big box, negative cosine 524 in pi final, which is 1 over 1, 5. Oop, ahead of myself. 1 over 524. That's our t. Divide that by 524 in pi. Do your best to look at the pattern. Don't get bogged down in what you don't know. I say that again. This is patterns you want to be recognizing. Unless you're working with somebody who knows their calculus, okay, and follow them. But You don't have to know this, calculus. You don't have to know how to do antiderivatives. You just follow the pattern. And I'll give you a similar function, all the same pattern. Okay, so this is then that. Again, final minus, it's the big guy out here. And then, of course, the cosine function itself has a negative. Cosine 524 in pi in the initial, 1 over 1048 divided by 524 in pi. A lot of stuff going on there, but just stay focused. Look back at it. Make sure you get the pattern. Okay, and the next, simplify things. So again, if I may do that, this is just to separate. This is the basic function that we're doing, and then we're breaking it up into pieces. And now we are going to simplify. This is going to be negative cosine. So again, this is going to be 524 divided by 524 because the cosine function operates on a radian, right? An angle. And these numbers are going to just relate to each other. And so we're just going to have this cosine function hanging out. So again, slight hesitation because I don't want to get into the weeds of why is it 524 or 524? Well, we're just going to put, just for the sake of argument, put the numbers together and we'll have it in pi's. So again, try to leave out as many extraneous details as possible. Cosine n pi. 524 divided by 524 is just 1, so this is negative cosine n pi. 524 n pi minus, this is going to be n pi over 2. Over 524 n pi. So that's why I separate that. And then there's the big bracket to hold everything. So this is the result of this stuff here. Cosine 524 n pi over 1 over 524, which is just 1. And so you just left with the cosine n pi. 524 over 524 is 1. Cosine n pi over 524 minus, cosine 524 n pi 1 over 1048 n pi over 2 over 524 n pi. Now let's put all the pieces together. We have our 1048s, and then we also have our 7/8 out there. Okay, so next screen. Un segundo, make sure I have my stuff is organized as I want to. 1 second. Well, it'll be literally 1 second for you. It might be 1 minute for me. All right. So it's less than 30 seconds for me, but can't confirm that. Anyway, I have all this written on paper. It needs to be organized or else it's going to be a super tangent. So, okay. So now I want to put all the pieces together. We had the upper bound integral, and now over here we did lower bound. So this to group together for 1 and 7/8. If you look back here, this was 1 times 1048, and this is 7/8 times 1048. So the 1048 is common, and so I'm just going to factor that out. And what we're left with is 1048. And then that leaves us with negative cosine n pi over 2 plus 1 divided by 524 in pi. Okay, remember where that comes from? No, I don't, Mr. Kelly. I don't remember, Mr. Kelly, where that came from. Okay, so it comes from here. Negative cosine n pi over 2 plus 1 divided by the common denominator. That's why this is here. Okay, and then this is minus 7. Okay, so then that becomes that. Okay. Second. All right, so this is that. And then that's minus 7/8. I think I'd be better off doing the next line. So that becomes minus 7/8 negative cosine n pi plus cosine n pi over 2. Okay, where's that plus sign come from? Where's this all this stuff? Let me just divide this and explain that. Okay, this is all together and big bracket. So you can see the 1048 was factored out. So this is understood 1 here, 1048 times 1, 1048, and distribute over here. This is going to be our 7/8 times 1048 that we see over here. So let's look back here at this result and why it translates here. So this becomes, not even looking at this, we're just inside. Negative cosine n pi over 2 over 524 n pi. Okay, that's common. They both share the 524 n pi's. So it's negative cosine n pi minus cosine n pi over 2. So plus cosine n pi over 2 divided by the common denominator 524. And of course, 7/8 is out here. And the 1048 is common to both. This understood 1 is 1 times 1048. And this is going to be minus 7/8 times 1048. Once again, why is that? Maximum, minimum. Breaking up the integral of this sound wave into 2 pieces to make the whole 1 over 524. Again, this particular part of the sound wave, you can imagine to be like the guitar string has been plucked up for half of a wavelength. This is half, and this is be a whole wavelength. Whole wavelength, half. And that half is the length of this sound wave. The length being 1 over 524 seconds. I know second space. Don't worry about that. 1 over 524. And so that's where that comes from. Maximum, minimum, and these are the results. All that now, let's do a final distribution just for making sure that we can see the whole picture, because I'm a holistic guy. Okay, so, oops. Okay, so this will be 1048. I'm now just distributing 1048. Negative cosine n pi over 2 plus 1. And this is going to be, so this whole bracket, minus, okay, 1048 times 7/8. I do that on the next line. So I'm just, all I'm doing here is I'm simplifying the algebra, but, you know, you guys should be able to simplify the algebra. But anyway, I don't take anything for granted. So I'm just being careful with these minuses. I'm trying to make things as easier on the eyes. So then this is going to be negative 1048 times 7/8 Okay. Multiply that by cosine n pi. Plus looking at my key here. And that's going to be plus cosine n pi over 2. I just distributed my negative signs. I took this outside. It's going to be 1048 times this. And then in order to maintain this as a negative, I just made this positive and then did likewise for the second term there. And again, that's going to be all of this is going to be divided by 524 n pi. Okay, so I'm going to just clear up the distribution there. So before I actually distribute this 1048, I'm going to just make this into a positive because it's going to be negative, negative. So this is going to be a positive. And then, let's see, let me just erase that, show you what I'm talking about. Okay, now we have another silly malfunction here. One more second.